All right. Good morning, everyone. We're going to go ahead and get started with today's webinar. So thank you for joining us for our Research Radar, Building a Greener Future from the Ground Up, hosted by the Minnesota Department of Transportation and the Minnesota Local Road Research Board. My name is Molly Yang, and I'll be your host for today. So we're excited to have our presenters, Emil Bautista, Jim Johnson, Terry Baldry, Raul Velasquez, and Jaren Iden joining us. So today's webinar is the 9th in our Research Radar webinar series, sponsored by the MnDOT Office of Research and Innovation and the Local Road Research Board. Each month, we highlight different research projects focused on a common theme. So just to introduce our two offices a little bit, MnDOT's Office of Research and Innovation manages over 185 research projects in progress that ranges from local initiatives to pool fund projects with other states and comprises both basic and applied research. We're here to help transportation practitioners determine whether new research is needed or if existing studies may solve your needs, recommend the best research methodology for your project, access local and national funding sources, and manage your project from start to finish. Our partner, the Local Road Research Board, is a city and county-run organization that sponsors research and educational initiatives that address local transportation needs. So you can stay up to date with our research by following us online and subscribing to our newsletters. We'll send you website and subscription links in a follow-up email after today's webinar. So for the fiscal year of 2025, we have funded 27 new academic research projects from a pool of 82 proposals. If you'd like to see the full list of projects, you can scan the QR code on your screen. If you have any subject matter expertise and would like to serve on the technical advisory panel for any of these projects, please reach out to our office. And with that, before we get started, I like to read the Tennyson warning. This session will be recorded for those who cannot attend. If you have enabled your camera during the session, the recording may include your image, which is private data under the Minnesota Government Data Practices Act. You are not required to allow MnDOT to use your image, and there are no consequences for declining to do so. To opt out of the recording, you may simply turn off your camera. And with that, I'd like to go ahead and introduce our presenters. So for our first project, we have Emil Bautista. Emil is a licensed professional engineer in Minnesota and currently serves as the sustainability engineer at the Minnesota Department of Transportation in the Office of Materials and Road Research. In this role, he leads MnDOT's Environmental Product Declarations Collection Program, playing a key role in quantifying the carbon footprint of construction materials. For our second project, we have Jim Johnson. Jim is a graduate of Iowa State University with a bachelor's in civil engineering. He has 34 years of experience in municipal and transportation engineering services. Jim currently serves as a part-time consultant city engineer in Chisholm, Minnesota, as road supervisor for Thunder Lake Town Board, and as treasurer for Northland Alliance Church. He has been married to Kat for 56 years with 3 children and 9 grandchildren. And for our final presentation, we have Terry Baldry, who is the aggregate base and grading engineer in MnDOT's Materials Office, where he specializes in aggregates, base, grading, and reclamation. In addition to his construction and materials duties, he serves as a technical liaison for research on recycled materials, pavement foundations, and geosynthesis. We also have Raul Velasquez, who is a geomechanics research engineer at the Office of Materials and Road Research at MnDOT. He is mainly involved in conducting geotechnical research with a focus on pavement foundation. He also provides geomechanics technical assistance to the MnDOT specialty sections and districts. And finally, we have Jaren Iden, who is also a geomechanics research engineer at the Office of Materials and Road Research at MnDOT. Her research focuses on the mechanical and hydraulic characteristics of geomaterials, advanced geotechnical modeling, and the performance of pavement foundation and rigid pavements. Her role focuses on connecting research with practice to support innovative, practical solutions that enhance the durability and long term performance of transportation infrastructure. And with that being said, I now like to pass it on to Emil to get us started.
Good morning. Share my screen. And let me know if you can see it.
Yes, you can see it.
Okay, perfect then. So good morning all. Just like Mali mentioned before, I'm here to present on one of our recent projects that deals with supporting sustainable procurement, in this case of concrete pavements in Minnesota. It's a way of linking materials, um, global warming potential, carbon footprint to project level decisions. This research project was kind of the start point for us, or is the starting point for us. Um, so when we look at, what are the benefits of this research that was conducted, the thing that we have to look at is what do we have in the state and the things that we need to do based on our status. And in 2019 and then later amended in 2023, there's status that 216H .02 that ask MnDOT or the state to reduce statewide greenhouse gas emissions across all sectors to level at least of 30% below 2005 by 2025 and 50% by 2030 and net zero by 2050. The legislation passed on 2023 and created an environmental task force that met for first time in October of 2023, and the task force is tasked with providing recommendations to the commissioner. By January 15, that the task force should, make the recommendations so the commissioner can establish and publish maximal acceptable global warming potentials. And the legislation calls for eligible materials, carbon steel, structural steel, concrete, or asphalt paving mixtures, and then eligible project is new construction or reconstruction of 2 or more lane miles. So when we're looking at ways to how do we track global warming potential, the document we're use in this case is what is called an EPD, an environmental product declaration. We're looking for a very specific document, which is a type 3 environmental product declaration. It should be product X specific environmental product declaration. It is based on a life cycle assessment. It should be third party verified. It should be standardized, transparent, and comparable. Within the same category of materials, and I might talk a little bit more about that after, and then it should be focusing on global warming potential as the key metric. On the right, you can see the way that, these EPDs have been depicted. They have been compared to what is called, nutritional facts on your food. And here what we're looking at is a concrete of 4,000 PSI, 1 meter cube of it has 317 kilograms of CO2 equivalent for global warming potential. Right now, we're focusing on that metric, although you have many other metrics below. But the key one that legislation is using is the global warming potential. Now, it is important to understand that we're looking at this through a life cycle, and we need to define those stages. The EPD at the moment are focusing on what is called this cradle to gate typical EPDs stages. You can see that on your left with the red solid lines. And it focuses on production. It looks at the constituent production. It looks at transporting those materials to the facility of production and then producing the material. That's A1, A2, and A3. There are other stages as well too. The construction stage, which is A4 and A5. A4 consists of transporting material from the gate of the producer to the project site, and then A5 is the construction operations. As I mentioned before, we obviously are now starting with EPDs, but the goal is that this can keep moving forward and keep looking at other stages in the cycle. Here is another way that I've seen around in EPDs document that we have received. It's a way of kind of showing it in pictures and graphs. This is for the asphalt side. Actually, you can see A1 materials, A2 transport, and A3 production, and they are just tied to that particular stage and accounting for what type of emissions we create on these three stages. So why is global warming potential and why it matters? Well, global warming potential is the most common metric in emissions reduction legislation, and is the leading indicator of our environmental impact of construction material. It is expressed in kilograms of CO2 equivalent. So what you tend to do is, for example, like methane or nitric oxide, the example is very clear there. 1 kilogram of methane is 36 kilogram of CO2 equivalent. So what you try to do is kind of normalize everything to CO2 measurements. What we have here, CO2 and methane, is what they call, or what we call, greenhouse gases. And cement production, we know, is a major contributor of global warming potential. The calcination process releases a lot of CO2 when it's converted to lime, and this process is heading to making clinker, which is the key ingredient of cement. Now, I don't want to put it in the way that it's a heavier global warming potential, and for that it's not good. Actually, what makes us also large is the amount that we use. We use quite a bit of amount to do our infrastructure, so that's another important point. And when we look at cement, for every ton of cement that we produce, we were emitting around 0.8 to 0.9 tons of CO2. And cement production is, I've seen around, is somewhere between 5 to 8% of the CO2 emissions worldwide. So that took us to do some research here at MnDOT to try to develop a process to be able to lower our global warming potential and our construction material, and being able to start looking at how a framework will look to tie that with pay items. This research work is done by Michelle Cooper and Amlan Mukherjee. I'm mostly here just transferring, what the great work that they've done for us here. So what were the projects here was to be able to support MnDOT's transition to a low carbon concrete procurement by being able to integrate global warming potential into project level decisions. The key objectives were to provide technical assistance for adopting EPD, well-informed EPD practice, support global warming potential reduction targets by defining EPD acceptance criteria and looking at regionalized incentive thresholds. It also looks at connecting EPDs to MnDOT existing incentive systems. And the scope of work was to be able to kind of propose a framework that will allow us to do that in specific, which is tie global warming potential into our procurement workflows and be able to align with the Minnesota Buy Clean goals as well too. During this process, we were able to pilot test on 5 MnDOT concrete project payments around the state. And we were able to also collect some other things too and accomplish some other important things too with this research. We were able to collect around 800 published EPDs relevant to Minnesota concrete. This research project also analyzed 32 MnDOT approved concrete mixes, collected data for A1 and A5. I want to make the note here, EPDs are A1 to A3, but we're looking at collecting also A4 and A5, and I'll explain that in the next slide. Data from 5 real world projects, so we look at 4 reconstruction and 1 joint repair. And, this helps us out to develop a life cycle information model to be able to estimate and map global warming potential, also perform benchmarking analysis to establish those limits, and also created a few tools that allow us to work with implementation of this research. Those are the 2 pagers and the submittal packages. We also have a proposed threshold for acceptance and incentive, and they have also mapped GWP to MnDOT pay items to align with procurement and incentive systems. And also develop models for estimating A1, A3 for mobile batch plants, and A1 and A5 for global warming potential for concrete pavement construction. So why am I talking about A1 and A5 now? When I said very clearly EPDs are A1 to A3, well, it's very simple. When we do our infrastructure, we don't necessarily, we don't procure a material. For example, for concrete, we pay for the placement of concrete. So we want to be able to track as well the amount of emissions that are emitted in the construction process, in taking that material from a plant to a project site, and the amount of work that has to be done on the project site with equipment and other things, and kind of estimate those emissions. Our legislation does not require us to do that, but we want to start looking at how that will look because of how it is tied into our to the way we pay for work. These two pagers, you can find them on a website. There's a very nice website that they created with a lot of resources in there. You can find introduction to EPDs and any other resources. Some of these resources are coming from federal government. I know now some of those websites might be inactive, but I think some of them are still accessible. You have also you can look at Minnesota benchmarking efforts, those initial efforts, and look at what they propose for global warming potential acceptance and incentive thresholds. Like I mentioned before, they estimated what is the emissions of A1 for global warming potential for mobile plants, and A1 to A5 for concrete pavement construction. And obviously, the big part of this is look at how can we integrate this EPD collection into procurement. So the EPD submittal package is just helping us out to ensure a timely and consistent environmental data collection to support benchmarking decisions. One of the things that they recommended was to maybe look at receiving this or requesting this document 2 weeks prior to material delivery, maybe at the end of the project or at the end of each calendar year. This is things that we're working with industry as we go. And on the special provision language that we have put together, we actually are looking at a time frame of 12 weeks after placement, just to get going and being able to collect as many EPDs as we can in this initial stage. Some in the implementations note that they had was recommended to have a separate project line item, so that there is an EPD collection type of item in the contract, and also information that provided that can be used then later to develop and regularly update benchmarking for threshold decision making. So why does it matter that we map GWP to pay items? Like I said before, we don't necessarily procure material, we procure a project, so it's important to be able to tie it to the pay items of the project will reflect the real work procurement and construction processes. It also aligns sustainability with incentives initiatives, and it kind of allows us to tie product sustainability, operational efficiency, mechanical durability, and environmental performance to incentives, and in this case financial and money decisions and life cycle decisions also as well. They did kind of determine some values that we can see around. You can see for concrete pavement, we can have around 58.4 plus or minus 13.2 kilograms of CO2 equivalent per square yard. This is concrete pavement placement. And then you can see that the structural concrete is significantly higher, but it's because it's by cubic yard. So these are two different units. This should not be compared. The same way that we shouldn't be comparing EPDs that even being for concrete, they are for concrete of two different type of specifications or strength level. Or so some of the key findings that we have on this report, and also some important mobile batch plants insights that we got. A1 stage, the dominant factor here is the cement. Like I said before, we know that it's worldwide. A4 and A5 stages can add around 17% to the total global warming potential. We did not find, or they did not find, any correlation with water cement ratio in GWP, and that's a very important correlation because it's a quality assurance measurement for us internally. And if I'm correct, we do have some incentive tied to water cement ratio requirements. Also, the global warming potential can be different for different scenarios, for a mainline paving or a turn lane or a joint repair. So we need to start looking more into those type of projects. We also have the mobile plants in the state, which I've been finding out some good amount of our producers have those type of plants. So they can be higher and more variable than ready mix production. A1 and A3 could be up to 66 kilograms CO2 higher, and ready mix threshold of limit may not apply. So we do need more data from mobile plants to be able to create in the future specific benchmarks for this type of plants. Some of the things that we were also able to get were stakeholder concerns and future needs. From side of the producers and the contractor, they showed concerns about how are we collecting the data and where are we storing it, because they have mixed design data tied to those documents, and they feel this could be proprietary data and they don't want it to just be openly shared. So we're looking at ways, how do we tackle this? How do we are able to have a good procedure or process to collect data and store it in an efficient way? We have to integrate this into spec and our quality assurance system and incentive to recognize the mobile plan variability and also they express concern about how are we going to do when there are times when we get mixed changes because they happen real time. So we're trying to work through those things with industry to make the adjustments that are needed for us to be able to collect this data, and also trying to define what a minimum project size or APD requirements could be. So for the future, we need more information on mobile plants and precast concrete. Uh, we are looking at doing benchmark by functional classes like other states have done. They recommended also looking at an audit program for EPD verification and being able to integrate quality assurance and sustainability data systems. Uh, this work aligns very well with the biking strategy of the state and the direction we're taking. It supports Minnesota Bike Clean pilot projects and also provides regionalized data-driven framework and build capacity for future GWP-based procurement. And it supports in the legislative content. It does support our requirements to set GWP threshold by 2028, and this applies to concrete, asphalt, steel, and rebar, and allows us to kind of lay the technical foundation to be in compliance with the state law. So where are we at right now? We have change orders on 9 projects to collect EPDs. We're looking at lettings from November to February for potential projects and reaching out to districts to start kind of having this conversation to include this into the contracts. And then we're also working with industry because we have realized there's a need for training on their part on knowing exactly what type of information they need to collect to provide to a consultant to create these documents for their products. On the right here, you can see some of the language that we have put together for a special provision that it should be making it into contracts in the near future. That's all I got. Thank you very much. If you have any questions, just let me know.
Right. Thank you, Emil. And next we will go on to Jim Johnson's. Right.
Thanks, Maylee.
Yeah. Let me go ahead and share my screen real quick.
Please. And while we're waiting, I'll just let you know my 34 years was with consulting firms in and around the Twin Cities, but I'm old. I've actually got 55 years of experience. So been retired for 12 years, so semi-retired. So thank you. Good morning and welcome, everyone. My name is Jim Johnson, licensed professional engineer in the state of Minnesota with registration number 12651. So you know I'm old. This study was under the leadership of Hale Silan with the Department of Civil Engineering, Construction Engineering, Environmental Engineering with Iowa State University in Ames, and they were in collaboration with the Highway Sustainability Research Center at the University of Massachusetts at Dartmouth in Fall Rivers, Massachusetts. Before I get started, I do want to acknowledge Tom Burnham, that's in the office, MnDOT Office of Research and Innovation. Tom served on our committee and quite frankly is much more qualified as a researcher to probably be presenting this information and answering your questions than I am. But with that, let's move on. If you would, Maylee, the next one. I just wanted to quickly share with you the project abstract to give you a little bit of background as to what was the focus of this particular research study. And if we can read real quickly, the limited local availability often constrains the growing demand for high quality aggregate materials in road construction. To address this challenge, recycled waste materials, including plastics, are being explored as sustainable alternatives. This study investigates the feasibility of incorporating recycled plastics into asphalt and concrete pavements to enhance sustainability and reduce landfill waste. And part of the study and follow-up to Emil's presentation was also looking at CO2 reductions and other environmental impacts. Maylee, if you'd go to the next slide, please. Just quickly going through the objectives of this study, as you see on your screen, just real quickly, it was to survey the use of recycled plastics for roads in coordination with literature research, other studies, field investigations, or infrastructure projects that have already been doing this. This study is hopeful, just the next step in progressing towards that utilization of hopefully recycled plastics into our asphalt and concrete pavements. As we see in bullet number 2, is to evaluate the feasibility of using plastics in paving mixtures, and then to work in partnership with MnDOT, because MnDOT provides a lot of the standards that we used in doing this study in terms of specifications, mix designs, those types of things. So again, work in partnership with MnDOT to provide a summary of the work being done both locally and within the pool funded studies. Those are the studies being done elsewhere, both nationally and internationally. And then hopefully in the process and in the future to continue to work with MnDOT and MnRoads to demonstrate the proof of concept for an economical and beneficial, both environmentally and, as I said, cost-wise, and to save some of our virgin aggregates or to be able to replace them in the future. Next slide, please, if you would, Maylene. The second chapter of this particular final report talked about the summary of the use of recycled products. And what I want to just share with you here, just very quickly, are the different types of plastics that are in major manufacturing and use in today's economy and our worldwide use of this. And if you'll pay attention, maybe because it will appear in some of the following slides, I always have a problem with acronyms. And here you see whether it's PET or PVC or PS or LDPE, just so you have a reference back as to what those acronyms actually stand for. But again, just showing just a portion of the large variety of plastics, thermoplastics and thermal settings that are available on a worldwide market. Next slide, if you would, please, Maylene. Chapter 3 of the particular study, or step 3 of this particular study, was a survey, interviews, and characteristics of plastic materials. This was a solicitation nationwide, internationally as well, to not only researchers, but to plastic manufacturing, plastic recycling companies. And what I want to share with you, just again for information, are these two graphs that were part of that study. The first one on the left showing the type and percentage of plastics produced and recycled by facilities and companies. As you see the percentages, and again, the acronyms on the left are those that are on the previous slide for your reference. And then not only the wide variety of plastic types, but the shapes and percentages, or the shapes or forms that these plastics are produced in, are on the graph to the right. And as you see, a wide variety from flakes to granules to pellets to strips to fibers and other forms of production as well. Let's see. Next slide, if you would, please, Maylee. Chapters 4 and 5 that we'll be going to now are really the crux, or the feasibility study, if you will, of the study. The chapter 4 being that on the utilization of plastic waste in asphalt paving. And then as we go on to chapter 5, which I'll get to in a few slides, we'll focus on the use of those plastic wastes in concrete material as well. Shown here on the left are the decisions that were made by Tom and the rest of the technical advisory panel based on their knowledge and utilization here in the state of Minnesota. And so we narrowed it down to the two sources of aggregate or plastics, I should say, that were to be tested on for incorporation into the production of asphalt pavement. They analyzed in the study, it doesn't show up in what I'm presenting this morning. They were looking at both a dry process, which is introducing each of the materials, aggregates, the bituminous, in their separate components, more like the batch plant or the bringing in each of the elements in that asphalt mix, as opposed to a wet process where the plastics are introduced into the bitumen mix, which includes the aggregate already. And for this testing and study that they did, they utilized the wet process. There are some real issues in introducing in both processes that are part of the further research or into the, as you go further into this study. But as you see, source one was this, it's the LLDPE is a linear low density polyethylene, was one source that was tested. And the second source is on the right, as you see, which is 50% high density polyethylene and 50% low density polyethylene. And then to the right is some testing results based on just, and it was using the standard MnDOT performance grades 58-28. The first one you see is just using virgin binder without any of these plastics added. And then the right two columns utilizing in the results, utilizing source one and source two. And you can review those at your leisure. They're beyond my expertise to tell you what they mean. Next slide, if you would. Thank you, Maylee. And then again, this is again showing some of the results of the different types of testing that were done on these three types of mixes, the virgin mix, then as well as the other two that incorporate the two plastic sources. One on the left is an asphalt binder separation study. Then you see the intermediate temporary temperature cracking performance evaluation with and without the plastic in the middle. On the right, you see the visual picture of what the pucks of both sources, the virgin mix, and then the second source, excuse me, the first source using the linear low performance, just the appearance of those. And then below that, the testing results from an ideal CT test results. Again, they're beyond my expertise, so you can ask Tom Burnham what they mean. Next slide, if you would, please, Maylee. The chapter 5 then, as I mentioned, was the study of plastic waste within the concrete paving. And basically, again, we have a standard mix that is our basis of performance testing. And then on the right side, you see 4 alternative forms of plastic, mainly in a fiber type that were used as testing of incorporating these different types of fibers or sand, as you will see in the 5th mix, and what those results are. The graph on the left is really a gradation formula that they were shooting for, so that portion of it, in terms of gradation, was in that range, trying to follow what they call that tarantula curve, but trying to follow the percentages as shown in red. And again, to the right, you've got the virgin plastic fiber on tree, which is just as manufactured. To the right of that, fiber 1 is a recycled plastic, as are fiber 2, and then a plastic sand as manufactured on the right. Next slide, please, Haley. And again here then, we wanted to show on the left the mix proportions, again following MnDOT design standards. And as you see, the leftmost column of the 5 is the control group with just using virgin aggregates. And then as you go to the right, utilizing each of those 4 different fibers or sands that we talked about on the previous slide. And then on the right, one of the first tests performed was, of course, on slump. You'll see a visual picture of that on the right, utilizing each of those 5 mixes, from the upper left being that control group, and then going across, down, and across again for the other 4 that we're incorporating the plastics, either as fiber or as sand. Then please, Maylene, next slide. Then what I wanted to share with you, without going into a great detail, on the left is the visual results of inches of slump that were pictured on that previous page. You can see how each of those batches or samples, what the results were in terms of slump. To the right, there was an evaluation of air content, again on those same 5 samples, or mixes, I should say. And you see those results. Next page, if you would, please, Maylene. Continue with the different types of testings that were being performed on these 5 different mixes. On the left here, you see the 28-day compressive strength test results. And then on the right, the 28-day tensile strength test results. Next page, please, Maylene. Continuing, then on the left, you see the 28-day flexural strength test results. And on the right, the 28-day electrical resistivity tests, which I know nothing about. And again, we'll have to refer to Tom for his expertise as to what those are. Next slide, if you would then, please, Maylene. The executive summary, as you know, is up front, but I wanted to use it as a conclusion to try and provide a little bit of oversight going from the abstract, going through the study, and what our findings and results were in a more concise process. As you see, and let me read along with you on these. The asphalt mix designs were developing using the wet process method, with various plastic concentrations tested for their impact on binder performance, cracking resistance, and moisture susceptibility. Bullet number 2, concrete mixtures incorporating recycled plastics as aggregate replacements and additives were analyzed for compressive strength, flexural properties, shrinkage, and workability. And then quickly summarizing the results, the test results on the plastic modified asphalt indicated a reduced cracking resistance of the mixture when post-consumer, which is not virgin materials coming out of the plastic factories, but those that are being recycled. Plastic is added to the binder using a wet process as compared to the same mixture with the same binder without plastic. So there was actually a reduction in the performance in the case of the asphalt mix. And then item 4, dealing with the concrete. Incorporating the plastic materials reduced the concrete's workability and air content, with plastic fibers further improving tensile, structural, flexural, and durability properties. While plastic fibers increased compressive strength, recycled plastic sand lowered it due to weaker bonding with the cement base. So, and then there was in the study chapter 6, which talks about the research benefits and potential implementation steps that can be utilized in moving forward with further studies and more refined studies. And then chapter 7 concludes with conclusions and recommendations for future studies. And with that, I have completed what I need to present at this point. Thank you.
Thank you, Jim. And next we'll move on to Terry and his team.
Hi, I'm Terry Beaudry, work out of the Minnesota Materials Lab in Maplewood, Minnesota. So today, I and my colleagues, Raul Velasquez and Jeren Aiden, will be presenting some preliminary findings on an LRB and MnDOT funded study. Next slide. Yep, the name of the study is Evaluation of Gravel Stabilizers Used on Gravel Roads and Gravel Shoulders. There you see the team, the project team. I just want to highlight a few people. The PIs are Bora Chetin and Anik Anktil. They're out of the Michigan State University. Then the panel members, I'll just highlight the three, those in green, who will be presenting, of course, myself, Sharon, and Raul. And then we have 9 county representatives on this project. I think this is the most I've ever seen for research with so many counties are very interested in this. So next slide, please. So quick background, in late 2019, I had visited Polk and Wilkin County in Minnesota. They had been using gravel stabilizers for about 10 to 15 years, and we're seeing some really good results. And they had given me some preliminary numbers of, really good savings in aggregate and in grading use. And I thought, well, geez, it'd really be great to formalize a study on this. So I put in an idea scale, and I think it got funded in, I don't know, 2022 or 3 when the study started. Some of the benefits, just a little bit more background. Minnesota has about 70,000 miles of roadway that are gravel roads, over 140, so roughly half of our roads are gravel roads. And then grading and gravel loss are probably the biggest cost drivers and energy drivers for gravel road maintenance and shoulders. And then some of the problems that we see on gravel roads are, of course, potholes, washboarding, corrugations, and those are the main drivers on when we're going to regrade the road. And then so we're trying to look and try to quantify, what impact the gravel stabilizers have on maintenance, because this really translate in less money spent on labor and equipment usage and also gravel. So therefore, the intent was to quantify those improvements, the cost benefits, as well as the environmental benefits, both fuel and CO2 used with those gravel roads. And here's just a nice illustration of, we have a gravel road on the left. And of course, if you look at a gravel road, there's usually about 2 or 3, 4 inches of crushed gravel on top of a compacted soil subgrade. That's how the road's made. It's not just the gravel, but you have a compacted subgrade, then 3 or 4 inches of gravel on top of that. And then many of our, especially of our rural bituminous roads, have a gravel shoulder anywhere from 2 feet to 8 feet in some cases. Then concrete, of course, we do have some gravel roads, or gravel shoulders on those. So with that, I think I'm going to turn it over to Raul. Thanks.
Morning, everyone. So in terms of field studies, the study locations, we selected, the research team selected locations in 5 counties: Polk County, Itasca, San Luis, Cass, and McLeod. These counties were selected to represent a wide range of traffic levels, climate, and gravel types. It's important to note that the stabilized road sections in each county were monitored to assess mechanical performance, cost, to do analysis on cost, and environmental impact. So in terms of materials, it's funny, this study come in 5s. They selected also 5 stabilizers, 2 non-proprietary standard stabilizers, which are magnesium chloride and calcium chloride, and then 3 proprietary stabilizers. Note that it's important to note that each stabilizer differs in chemical composition and recommended application dosage. So in this slide, it shows recommended by the manufacturer, the dosage that was used for building the sites. It's important to know also that the different chemical composition from each chemical stabilizers will influence performance, it will influence the environmental behavior, and it will influence the effectiveness of these kind of stabilizers in road performance. And we'll show some high-level results in the next few slides about that. Field testing was conducted on a total of 28 sites, so pretty comprehensive study. Again, across 5 counties. The mostly used stabilizer for this study was the standard ones, so calcium chloride and magnesium chloride were the most common use applied stabilizers for this study. Note that this test matrix is pretty diverse and comprehensive, and it allows us to really compare performance of these stabilizers with different conditions, different dosages, and different construction methods. So that's very good for us because it accounts for the variability that we face across the whole state. So this is an example of the sections that we're constructing as part of this study in Cass County. 7 sections of a 1/4 mile were built using the stabilizers shown in this schematic. The treatments included the use of Dustex base 1, permazyme, magnesium chloride, and some combination of those. Here an example of the construction processes that counties do use for applying this type of chemical stabilization. So you have first stage, you have the ripping of the granular material, then application of the stabilizer via injection, and then mixing, grading, and finishing, and then compaction. So now I'm going to provide just big picture results, big picture summary of what we have getting so far. Again, Terry mentioned this study has not been completed, so it's still in progress. So in terms of mechanical performance, there has been done a lot of research for past decades on this topic. So I'm just going to briefly mention some of the positive results, and then I'm going to give it back to Sharon, where she's going to talk about the environmental impact and the positive results we're getting out of that analysis. So in terms of mechanical performance, stabilized sections after being subjected of a freeze-thaw cycle, after going through a winter and a spring cycle, show positive results in the sense that the performance has been reduced less when you have stabilizers. So basically, the impact of shear strength by measuring using DCP, reduction using for the control sections, the reduction in performance is about 70.2% on average, where the stabilized sections only have a drop in performance of about 11%. In terms of stiffness measured by the LWD device, again, the control sections show a reduction after going through a freeze-thaw cycle of about 17%, while the stabilized sections have a reduction of 9.9%. So there is some positive results regarding mechanical performance. In terms of cost savings, researchers have shown that based some of the additives reduce cost per mile of about $4,000, so the base one. And then the classical standard calcium chloride provides a savings of about $3,000. So it's showing some encouraging beneficial results in terms of finance. Now, in terms of environmental impact, I'm glad that Emil talked about what global warming potential is. So it simplifies our discussion here. So stabilized sections show up reduction in GWP up to 4.6 kilograms of equivalent CO2 per cubic yard. In terms of cost savings, up to $5 per cubic yard of material being placed. Also, the research team measure water quality and toxicity of these materials. Unfortunately, all of them meet US EPA water quality standards, and there has not been, so far the testing results show no acute toxicity to any aquatic organisms by using these stabilization materials. And now I'm going to give the floor to Sharon so she can talk a little bit more about the environmental benefits, a little bit more details on that and provide more examples. Sharon?
Thanks, Raul. So we thought that it would be good to show some of the examples how actually we got these numbers that my colleague Raul just shared with you. And before, introducing this small examples, I want to emphasize the scope of the study. So we had 5 counties and we had 64 sites of maintenance data, which is actually corresponding to over 300 miles of gravel road data, which is extensive, coming from 2005 till 2023. So here, big, thanks to county engineers, and it's actually showing a good, collaboration between the researchers, spec owners, practitioners, and the counties that, we were able to get this, and the research team was able to get this information. So we have increased confidence in our results that we're going to just show you now. So we have 5 counties, and we wanted to choose San Luis County for this presentation. We can go to the next one, Raul. Thank you. Because this is one of the counties that is contributing with the largest mileage of data. And right now we are looking at the maintenance cost for this county. And although it looks crowded because there are 11 sections in total which use base 1 and calcium chloride, we are practically looking at the before stabilization and after stabilization maintenance cost per mile per year, including the equipment, labor, and the gravel costs. And we can see that overall the cost of the maintenance is decreasing after stabilization, regardless of the stabilization type we are using. And if you look at the same data in a different way in terms of the average savings, we can see the breakdown on the right-hand side for base 1 and calcium chloride. Again, for the equipment cost, labor cost, and the gravel cost, we can see that base 1 is yielding higher savings, annual savings, compared to the traditional one, although both they are, substantial savings when you look at this actually for the long-term economical impacts. We can go to the next one. So and this is a cost savings summary again, but in a bigger picture. We just talk about the yearly maintenance costs at the top, and this chart also has the public use savings and the production and the major rehabilitation breakdown for the different types of stabilizers: magnesium chloride, base 1, and calcium chloride, compared to the untreated control. And with this results, we are seeing that all stabilized sections, regardless of the type of treatment use, have cost savings compared to control. And we can also, say that the highest saving is in use phase, where actually the public gets the most benefit out of these treatments. We can go to the next one. So the first part that I just did was about the economical, and now we're going to look at the environmental benefits. And this one is going to be the comparative study between San Luis and Cass counties to actually consider all types of treatments that we have been talking for this study: calcium chloride, base 1, and magnesium chloride. And the researchers have looked at 3 key indicators of environmental impacts, which are global warming potential, cumulative energy demand, and water consumption. And it is important to know that this comparative study just modeled a mile-long gravel road with 4 inches of thickness, either stabilized with these materials that we have been discussing, or untreated, which is named as control. After introducing these unit sections of gravel roads, it's also very important to mention that the researchers have included each step of this gravel road construction, from raw material to production, from the major rehabilitation to public use, and then the yearly maintenance and end of life. So this flow chart that we are looking at, which looks a little complicated, is actually showing us our inputs on the left-hand side and the steps of, or the processes that this gravel road has within its lifetime. And then by inputting these, we obtain this outputs, which is we're gonna look at and see what the benefit is for us here. So to be able to do this environmental analysis, we have inputs. And again, these inputs are coming from this extensive maintenance data over, 20 years or around 20 years, field observations and, site observations that counties have shared with us. So we are looking at this entries or the use of gravel or the fuel for, again, unit of 1 mile gravel road. Although there are so many numbers here, I think it is important to mention that if we look at here, we'll see that the regraveling frequency under major rehabilitation is dropping for any kind of treatment gravel roads. And if you look at the maintenance part, which is at the bottom, we are seeing a huge and significant drop in the use of gravel for the maintenance, for the routine maintenance. And this part is really important for us. First of all, we are conscious that our sources are depleting, meaning that we don't have as much as gravel sources that we had yesterday. So we need to be aware of that these materials are limited. And when these materials are limited, they are getting more expensive because it is difficult to reach them. And also the hauling distances, bringing material from location A to location B is also creating a big environmental cost and, economical burden, because within the close proximity of this gravel road construction, there might not be enough gravels to support this entire construction. So it is really important for us to see this, huge drop in terms of use of gravel, and that also translates itself to the fuel consumption and less fuel consumption when you use the treatment, regardless of the type of materials, the type of treatment materials you're using. And this is coming from the real data from our counties. And again, no material is perfect, meaning that when you are producing this sustainable materials, providing sustainable solutions, you're also leaving marks in the environment. And the way to see it is looking at the global warming potential and the cumulative energy demand. And we're seeing gravel, base one, calcium chloride, and magnesium chloride. And we can see that base one is showing less environmental impact or the contribution to warming potential or energy demand, mostly because the production of the traditional treatment types we are using requires coal to produce heat for their production. So when we use these inputs coming from our maintenance data, plus this, materials EPDs, which are telling these parametrics, we can see the results in the next slide. And it looks like a crowded slide, but it's actually repeating the same thing for three key indicators, which are global warming potential, energy demand, and also water consumption. And in the high level, regardless of the type of the treatment, we are seeing that all stabilized sections have lower greenhouse emissions, lower energy demand, and lower water consumption compared to their controls. And if we even look at more details, we can see that, base one is actually superior with the highest savings. And with that being said, I'm going to leave the floor to Terry to wrap this presentation for us.
Yeah, so just, going back to our summary slide, I think Raul presented this before. It's a preliminary study. We're seeing some cost savings, significant cost savings, and significant fuel and global warming gas savings. And so far, the water quality looks really good, and no toxicity to aquatic organisms. And finally, I'd like to, again, thank our partners on this project. Of course, Michigan State is the lead agency, as well as the board and the 5 counties that are listed there. So with that, thank you very much.
All right. Thank you, Terry, Raul, and Jaren, for wrapping us up. For those of you that can stay, we will stay on for a little bit for a Q&A section. Feel free to drop your questions down in the Q&A chat or unmute yourselves. And with that, I already see a couple questions for Jim from Christopher. Some environmental regulatory agencies are concerned about the use of plastics that degrade and enter the environment. Did the project assess the use of additional plastics in pavement and later degradation and transport into the environment relative to baseline levels, or might that be evaluated in the future? So,
Yes, it was studied in the study, or addressed in the study. They were looking at potential environmental impacts and doing some projections as well. And it's included in the study, so I would encourage you to go into that study, and it is addressed, yes.
all right. Looks like another question for you, Jim, from Luca. Very cool research. Was end-of-life disposal considered in potential applications? Seems like there could be a lot of benefits to using PCR plastics in roads, but the potential problem of microplastic leakage into culverts and ditches also came to mind.
If I remember correctly, those were addressed somewhat, probably not in a great detail, but it was discussed in the study as well. Quite frankly, my interest in this was a study that I brought forward that got selected by the local research board, and that was utilization of the plastics in the aggregate base. I got promoted to this study in the paving materials, but yes, that was addressed in the study as well. So again, I would encourage you to get the study and review it, please, for that information.
So it looks like we have another question from Christopher. I believe this is for Terry and your team. Where can I find more details on acute toxicity methods used by this study? Um,
Are they have we addressed those yet, Raul? Or has the team addressed those yet?
Yeah, we have a task force report.
Oh, task force.
About 100
Okay.
pages with all the detailed testing we can share.
Sure. So send us an email and we can get you a task force report.
yes. All right. And I guess I have a question for you, Emil, about that GW submittal package. Who would be responsible for submitting it? Is it the manufacturer supplying the materials, or is it the agency purchasing it?
It should be the manufacturer. So if
The manufacturer.
Yeah, it's a document that the manufacturer will use information from their production, how much energy they use to produce, even mine materials. To mine materials as well, too. So it's the submittal package is something that the contractor or producer needs to provide us, the agency.
Okay. Good to know. Thank you. All right. Any last questions? Please feel free to drop them down in the chat. All right. Well, we are at 11:05, which is a little over time. So thank you all who have stayed. We will send out resources and links to everything shared in today's webinar in a follow-up email. And with that, that concludes our webinar for today. Again, thank you all so much for attending. We hope that we'll see you in our future Research Radar webinar series.